Hi everyone, thanks for joining my talk. It's the last talk at the summit, so thanks everyone for joining. Okay, so let's get started. My name is Michael, and today we will be talking about model alignment at scale on Databricks. And we have prepared this talk together with Ryuta and Alex. Both of them are specialist solutions architect, also at Databricks. Okay, so let's get started. At first, we will discuss what is model alignment and why we actually need it. And after that, we will discuss different algorithms we can use for that. So we'll start with the reinforcement learning with human feedback. And after that, we'll discuss what we can do with the reward model, how to get rid of it. And finally, we'll get to direct reference optimization, so another interesting algorithm. And after that, I'm going to introduce a solution accelerator for model alignment. So that's a project which you can clone. It's available on the GitHub. So you can just clone it, adjust to your actual business requirements, preferences, and run it on Databricks. And I also have something like an example scenario. So I will share the scenario with you, how it's working, and also share the metrics and the test results. Okay, so let's get started. What is model alignment? At first, let's discuss the typical large language models project. Usually we start with the use case, and we need to define evaluation data set. So we can maybe go for some metric, standard metric which is available in open source, or we can define our own evaluation data set and then implement this metric calculation. After that, after we have the metric, we can of course compare multiple base models and pick the best one, the one we want to use. And after that, we come to this adaptation phase. So we'll have to adapt model to our requirements. And if it goes well, we can actually test and deploy it. So now let's discuss what actually model adaptation is. So usually we have three components here. We can start with continued pre-training. That's something we want to do if we want our model to learn, for example, new language, new domain. Maybe we kind of would like a model to adapt to some specific vocabulary, tone, language tone, something like that. After that, we can create our instruction fine-tuning data set. And do instruction fine-tuning. That's how we can let the model learn the actual task. Because our task can be different. It can be text generation. It can be maybe summarization, maybe something different. So that's where we let the model learn that. And if our requirements are, let's say, very complicated, we cannot just express them with the instruction fine-tuning data set. In that case, we need to do an alignment. I can give you a couple of examples when something like that might happen or might be needed. So usually alignment is done if you want the model to behave safe, maybe to generate helpful results. And that's kind of like a very complicated thing to do. There are also a lot of cases when we have actually quite simple requirements. For example, let's assume we are working for a, say, grocery chain for vegetarians, and we don't want our model to recommend dishes or ingredients, recipes with meat, right? Or maybe we are working for an airline and we are developing a chatbot for the destination recommendation. So in that case, probably we don't want our model to recommend some destinations where our airline doesn't fly. Of course, we can do it with a RAG, but probably to make sure that exactly in that case, our prompt is honored and it's actually doing what it needs to do, we might need to align it. So now let's discuss how we can do it. So reinforcement learning with human from the human feedback is the algorithm that was first used by OpenAI for the alignment. They have introduced it in the InstructGPT paper. And basically, it contains three basic steps. It starts with instruction fine-tuning. That's exactly the same fine-tuning we have already done. I just added it here kind of to because it was written in that way in paper. And after that, we have two new things. At first, we have a reward model. So we have to train a reward model, which can actually say if the generated text is good or bad. And after that, after we have our reward model, we can actually use a reinforcement algorithm to optimize, to tune our model. And usually people use, in most cases, proximal policy optimization for that. So in short, PPO. That's what was, I think, used by OpenAI. They might be using something different right now, but I think it's something they were using at first. And now let's discuss the reward model. So in reality, a reward model is like, it can be a classifier, it can be a multi-class classifier, it can be also a regressor. What's important is that the reward model can generate our rewards, right? So give some scores, which allows the algorithm to understand which answer is good and which answer is actually not good. And we can implement it in a very different way. We can use a very big large language model here, or we might be able, even in some cases, to do it using BERT, some BERT derivatives. I think in most, like for different use cases, it's going to look very differently. And now, after we have our reward model, we can implement actually the reinforcement learning part. And small recap, in reinforcement learning, usually we have an agent or reinforcement learning policy. That's usually a deep learning model which we're trying to tune or optimize, and we have an environment. So if we are kind of playing Atari games, that's going to be like simulator of those games. But we are not playing games here, we are trying to optimize large language model. So our agent is going to be the actual large language model, which is going to generate the text. And our target environment, let's say we can call it LLM context, it's going to have like the question and everything we have generated. So the agent is going to take an action, so generate text, and then we get a reward by using the reward model. And another quite important thing, what also might happen, it has happened to me, I think actually it happens to everyone. If we use PPO, our model can learn something completely different. As an example, it can start generating some weird symbols. If kind of our reward model is created in a way that it gives a bigger reward in that case, the model will learn it and it kind of stops learning what we wanted to learn. It will learn basically how to hijack the function. So how can we overcome that? To overcome that, we want to have two models. We will have one model which we are going to tune, and we will have another model which we will call a reference one. So it's kind of going to be our vanilla model, which we are not applying gradients updates to this model, right? So it's not changed. So what we do next, we generate the text by both. Like both models will generate the text, will answer the question, and after that we get two probability distributions. And what we want to do is to calculate the distance. And for that, we are going to use Kullback-Leibler divergence. So that's basically the way how we can measure this distance. And that's going to be our penalty. So very often it's called KL penalty. And basically, our loss function is going to look in the following way. We get the reward minus our distance or KL divergence. Now let's put everything together. So now let's say we sample our question from the questions data set. We generate one response by the reference model, another response by the model we are tuning by our policy. We calculate this distance, and we also calculate the reward using the reward model. And then based on that, we use our reinforcement learning algorithm to calculate the policy gradients, which we can apply to our policy or model we're tuning. And as I already mentioned, oftentimes we are using here PPO. It's like an on-policy reinforcement learning algorithm, very popular, supports both discrete and continuous action spaces. So we can basically do whatever we want here. It scales really well. And another point, we don't need to update all the layers of our model. We can freeze some of them, In some implementations, we can even do it in a way that the model we are tuning and the reference model will share some layers. Why it's important? Because in that way we can save GPU memory, which usually is a big problem. Okay, so now we can do RLHF. It's great, but we have still a couple of issues. This feedback dataset, it's not easy to get it. If we ask humans to create this dataset, probably we will need to ask multiple people to give the answers to the same questions, because like people usually give different answers. So it's a long and cumbersome task, and it's also usually quite expensive. And generating preference datasets, it's possible, and actually we will do it later, but it's not straightforward. So what we can do instead, we can use existing large language models, of course the bigger one, as the reward model. So we can do different things. So we can just use a large language model to calculate the preferences and then use that to train a reward model, or we can use it directly. So in this project, we are using it directly. So basically, instead of like having some reward model like in memory, we just call an API with some big model and just ask it to give the score. And in this case, it's working really good. But still, PPO is very resource intensive. As I mentioned, if we are optimizing 8B model, it means we will actually have two 8B models in our GPU RAM, like one for reference, another one for the one we're actually optimizing. And it's very hard to get the right hyperparameter combination. And if we have time, I can show like what can happen if that goes not in the right way. And of course, still we need the reward model. So there is another algorithm called direct preference optimization, and with this one we don't need a reward model. So what it does, DPO aligns large language models with human preferences by directly optimizing the model's policy using paired preference data. So what paired preference data means, it means just we have a good answer and we have a bad answer. And in that case, with this algorithm, we don't need a reward model. This algorithm is a lot simpler. It's easier to run. It requires less resources, and it's way less. Basically, it's not complicated to get this like hyperparameter combination. In most cases, it just runs. It's very similar to just a simple fine tuning. The only kind of there are multiple issues with it as well. One of them is that we still need a reference model. And there are a number of other algorithms which have arrived later, which fix a lot of issues that DPO has. And it's basically very easy to switch from DPO to those modern alternatives. Okay, so now let's discuss the practical example. So with the Model Alignment Solution Accelerator, you can easily clone it, and you can adapt it to your actual business, like to your requirements, to your preferences, and directly run it on Databricks or on Mosaic Cloud. And here is the example which we are going to implement, or which we have implemented in this solution accelerator. So let's assume we are working for the grocery chain, which primarily has vegetarians as customers. So for our chatbot, we want our chatbot not to recommend any non-vegetarian ingredients, recipes, and so on. So let's see how we can do it. And here we will use two algorithms. We will use PPO and we will use DPO. And we will also use large language model as a judge approach to evaluate the final resulting model. So how do we approach that? At first, we will select a bunch of topics, and using those topics, we will generate the questions. Of course, the topics are kind of going to be about food and dishes, food preferences and things like that. After that, we can deploy our reward model. So on Databricks, we can create a provision throughput endpoint, or we can use like the endpoints which are already there, and then we can use PPO for the training. And if it goes well, we can evaluate our trained model and test and deploy it. With DPO, our pipeline is going to look like very similar, but here are a couple of differences. So after we generate the questions, we will need to generate good and bad answers. And for that, we will also use large language models. And for the actual training, we are going to use TRL library. It was implemented by Hugging Face. It's a great library. It has already implemented multiple of algorithms. It has PPO, it has DPO, and it has a lot of new alternatives. And we will be using, tuning with both PPO and DPO, Llama 3 8B model, and we will use Llama 3 70B as a judge, and we will actually use the same model, like 70B model, to generate the data and to do the final evaluation. And we will actually do full fine-tuning, and we will try the low rank adaptation as well. So full fine-tuning means we're going to update all the weights we have in our model, and LoRa means we just train or fine-tune a small adapter on top of the model, which requires less GPU memory. Okay, now let's talk about data generation. So, as I mentioned, we will generate question and answers using Llama 3 70B. And for this batch question answer generation, we can use multiple approaches. If we don't need a very big data set, we can use Databricks Foundational Models API. We can use paper token endpoints, and they are really fast. It's very easy to use them and to generate the data with that approach. If we are going to generate a bit bigger data set, in that case, we need to, probably it would be better to use provision throughput endpoints, because it's your endpoint, you own it, you can scale it as you want, and you can use that for the kind of medium data sets. If you're really going to do something kind of complicated, it might make sense to run a cluster on Mosaic Cloud with VLLM. Probably in most cases, the provision throughput endpoint way is the best and the easiest. So now coming back to the last data generation question. So I said that it's not straightforward. So even Llama 70B does not is not able to answer all the questions right from the very beginning. Not in most cases, but in like maybe around 50%, 40% of cases, it produces wrong answer. What we can do about that? To overcome that, I have implemented the following strategy. So after I generate the first answer, I have a for loop, which I think does 4 iteration. And what we do, we use the same prompt, which we are using for as a reward model, like for scoring. And I'm asking Llama 370B to check if this model, if this answer is good. So if it contains non-vegetarian, unfriendly things. And if it does, I have another prompt which just says, please improve. Like, here is an answer. It contains some vegetarian unfriendly things, so please improve it, make it vegetarian friendly. And in most cases, after a couple of iterations, it really improves. But that takes time, and of course it means that you will be using your GPU machine not for a long time, but for a couple of hours. And also I'd like to mention that we don't need that step for the PPO. We need this question, like good answer and bad answer, only if you want to use DPO. And for the model evaluation, we are going to use LLM as a judge approach. So we are using Llama 3 as a judge, and in real scenario, probably we want to use a bigger model. And of course, it's really recommended to, after you get your final result, final model you're really happy with, to actually ask domain experts to kind of take a look at it. So here are the results. As I mentioned, we have generated 10,000 questions and use this 10,000 questions for the PPO and DPO tuning. And you can see that that full fine tuning with PPO gives the best results, closely followed by LoRa, and like the difference to DPO is very small. So the like how I understand this result, it just means that both algorithms can solve this problem. I don't think that based on these results we can make any conclusion which algorithm is better. I'm just trying to show that in both cases we can relatively easily get to a nice model. And also this like very small, like 1-2% difference is not actually a lot. And if we come back here, we can actually see that the variance is like actually bigger than the difference. Okay, so that concludes kind of the slides, my first part of presentation. Now let's actually look how all that is implemented. So probably we can start with looking into the results. So basically that's like my ML flow, and here you can see the models we were looking at. So like if you go back, you can see that I have actually multiple runs, and in reality I have multiple pipelines. So I have a pipeline for data generation. So maybe let's switch here. So here is the repository. So that's like an open repository. So you can clone it and run it in your Databricks workspace. We have here notebooks which we use to kick off the jobs, and we have here YAML configuration. Actually, also very important thing, the version I'm kind of presenting is not the one in main branch, it's V2. We will make like a full release and update the main branch shortly, but for now it's V2 branch. So if we go to YAMLs, we can see we have here accelerate YAML, and we have a bunch of Mosaic YAMLs. So those YAMLs are used to kick off the jobs on Mosaic, and I will go into that a little bit deeper in a moment. So I have checked out or cloned the repo in Databricks, so you can see it's exactly the same repo. So now let's look which notebooks we have. So we have first notebook, generate prompts. So that's the notebook which we can use to generate questions. And here you can see those topics. So probably if you want to adapt it to your use case, you can just change the topics and also change the prompts. So you can see the prompts are also here, so it's very easy to update it and to update it with your particular requirements. And then after that, if you want just to run PPO, for that we have another notebook. What is it going to do? So we will just read this YAML, and then we will kick off the run on Mosaic. So I can show you the YAML. So that's how this YAML looks like. So like we have here the name of the cluster, and we are requesting 8 GPUs. And basically that's the command line what's going to happen. So nothing really fancy here. We just install all the requirements. We, after that, download the dataset, and then we use accelerate to run the distributed TRL training. And we can also look into the actual script for the PPO. Oh, sorry. So also nothing really fancy here. So we have to create the PPO config at first. And after that, if you want to use LoRa, we need to define the target modules and to create the LoRa config. And then we load the model. And after that, we have to define the optimizer. So in this case, I'm using Adam. And after that, we can just create a PPO trainer, and we can pass the model we want to tune and the reference model. As I mentioned, we can create the reference like we can create a reference model from scratch, or we can create the reference model in the way that it's going to share some layers with the model we are tuning. In that case, we will use less GPU memory, and that's important thing. So that's the arguments we are using for the generation. And after that, we basically have the training loop where we are training of the epochs, and after that, we are iterating over the batches. And after that, we are generating our like the answers to our questions. And after that, we are calling our LLM to generate rewards. And after we have the rewards, we are so after we get the rewards, we just call the PPO trainer step, and then we also do some login to MLflow. Okay, so now let's look probably into the actual metrics, how the MLflow run looks like. So that's the experiment where I'm logging. I have logged all the runs, and probably we can take a look at this one. If you take a look at the model metrics, we can see here a lot of different metrics. So now let's discuss the most important metrics. So we have mean reward, and we have the rolling average. So if you take a look at the mean reward, we can see that at some point our scores start to actually like around between 2 and 4, which is actually really good. And you can also see that our rolling mean reward is also getting bigger. So I'm just calculating rolling mean reward over the last 10 steps. And another important metric is our KL divergence, which we have discussed earlier. So it should never be like, it's not a good sign if it becomes negative. So usually if it becomes negative, your training run is not going to do good. So basically keep in mind, just take, if you do the training, just check it from time to time and see if it's actually positive and if it's not too big. Like 35, maybe it's actually a bit too big, but this model kind of works in a good way. But maybe if it's going to be, I don't know, 100 or 1,000, that's definitely going to be a bad sign. Now let's take a look at the evaluation results. So here we have the evaluation of this full fine-tuned model with PPO. And if you go to artifacts, we have here a JSON file with the actual results. So we have our questions. Okay, I can make it a bit bigger. So we have for example, a question, and we can check out the output, and we can also see the justification for the response. So it says that it's 1 because we don't have here any meat ingredients. So for all the evaluation runs, you get such a JSON file which you can analyze and check out. Okay, let's really quickly look into the DPO. DPO looks in a very similar way. We have a lot of arguments. And actually here we're creating DPO config with all those arguments. And after that we have a DPO trainer. And here we even don't need to implement the training loop. We can just say DPO trainer.train, and it's going to train our model. And that's basically it. So as you can see, the implementation for DPO looks a lot simpler. But of course, we need to generate questions like good and bad answers, which in reality might be challenging. And last bit, what I actually want to show is actually inference. So basically, that's the prompts which we are using for the rewards. So basically, this is a system message that we send to Llama to ask it to score our like generated text, and that's actually like maybe the most important prompt here, because like in reality your reinforcement learning training is going to work nice only if your reward function does the right job. So maybe if you specify the reward function the right way, that's kind of more than 50% of the whole project. And as you see, we just ask it to generate the scores between 0.01 and 0.99. And we have also a couple of examples. And after that, we just call the foundational models API on Databricks. And that's pretty much it. By the way, the last piece, in reality, when we transform the score to reward, we like actually we take a logarithm of this score generated by the like our reward large language model. Okay, that basically concludes my talk. Please, if you have a project where you need to align your model, you can clone the solution accelerator using the following command. You can use the v2 branch, and you can adjust the prompts, adjust the dataset generation, and basically run it using Mosaic or Databricks. Okay, thanks everybody. Are there any questions?